Hey guys, welcome to lecture number 15 in the Math 4000. Like I said, I would like to continue with something new, and I will start talking about integrals. And this part, so this would be lecture number 15, you see I'll cover more than usual. Probably I think integrals will be covered in probably 3 lectures and maybe 2 recitations according to my estimates, but anyway, to say the least. And I would like to start with something that's, well, a little bit more basic, and you learn about this in Calculus 1. And this is called the Riemann Sum. So we'll talk about the Riemann sums and continuity of the definite integral. So I will not waste my time with any indefinite integrals. Basically just computing the antiderivative. I think it's much more important for you to know what happens with a definite integral. And let me start with the Riemann sums first, right? So the definite, let me draw a picture so that you already know from Calculus 1, and from Advanced Calc, those of you who have taken it. So let's just say that we have the graph of the function is like this. And let's say that the function is defined on this interval AB, right? And so this is y equals f of x. And this guy here inside, so this area here will be nothing else than just the integral from a to b. So this guy here is the integral, this number, the integral of from a to b of f of x dx. So this will be a number. Well, what was the Riemann's idea? As you can see, this is the area under the graph of f with the x-axis. Well, Riemann's idea was to approximate the area under the graph, right, by a family of rectangles, right? So basically, we're gonna just approximate this by rectangles, and we keep going like this, and so on, right? So you approximate this in this way. Well, maybe this is not the best approximation, but you can still do it, right? And you cover the area of this. As you can see, there is something left out there. There are some other ways of approximating this by using trapezoids and or a combination between rectangles and trapezoids and so on. But anyway, I'm not going to go into that. All right, so that was the Riemann's idea. And when this rectangle, so let me write this a bit. So Riemann's idea was to approximate the area under the curve y equals f of x, right, by rectangles. All right, so as you already know. And when these rectangles have, when these rectangles have equal width, right? The approximation of the Riemann sum, so the approximation of the Riemann sum reads as following. And the way we are gonna read this, we'll read it as in the as following. So we will read this as the lim as n approaches infinity of 1 over n, right? Times the sum, and I think, sorry, here it's b minus a over n, because it's from times the sum from k equals 1 to n of f of ck. And this will be nothing else than the integral from a to b of f of x dx. And here, I'm going to specify a bit who this, who these numbers ck are, where these numbers ck, they belong to this interval, this closed interval a plus k minus 1 over n times b minus a, and a plus k over n times b minus a, right? So this is how with the famous theorem of Riemann. And now I would like to illustrate this through an example. I think we have discussed this sequence. So an example. I usually discuss this in any advanced calculus or introduction to analysis course. So compute the limit. And now, so the limit as n approaches infinity of the sum from k equals 1 to n of 1 over n plus k. Well, we have seen this before, and I think I told you that we can solve this, well, find this limit by using that gamma n sequence, Euler sequence. Okay, now we would like to use something, well, with the Riemann sums. So the way we're going to do it is in the following way. Well, this can be also written as the limit as n approaches infinity of 1 over n plus 1 plus 1 over n plus 2 plus all the way plus 1 over n plus n. Right? So that's what we have to compute. So let's denote this sequence by xn. So this would be n plus k. Let me stick to the. All right. And now we would like to write this as a Riemann sum so that it will make, so that it will look something like this, right? As this formula that you see above. And the way we're going to do it is in the following way. So in our case, A will be, I would like to define a function on the interval 0, 1. So maybe I should think of A to be 0 and B to be 1. So maybe I should take out 1 over n. And here, this would be 1 over, and now I take 1 over n, so this will be 1 plus k over n. All right, that's great. So this is the Riemann sum. This looks like a Riemann sum. Okay, let's write this, which looks like a Riemann sum. All right, great. And now what we're going to do is to consider the function so that will be associated to this Riemann sum. So consider the function f defined from 0, 1, real value, f of x to be 1 over 1 plus x. Clearly this function is which is continuous and therefore Riemann integrable. F is integrable, right? Riemann integrable in the sense of Riemann. All right. And now what we're going to do is to consider the division, and this will consider the equidistant division of the interval 0, 1. And the way we're going to write this is the following. So delta would be x0, which is 0 over n. So this would be 0 less than x1, right? Which in our case will be 1 over n. Let's write it in this way, right? Which is less than x2, which is 2 over n. And we keep going all the way to, let's say, x sub k minus 1, which is k minus 1 over n, less than xk, which is k over n. And we keep going less than, what was the last one? xn, which is n over n, which is 1. So that's the division. We start from, so this is 0. As you can see, this is equidistant of a division of the interval 0, 1, because the norm delta of the division, delta, is given by, and we're going to write this in the following way, delta n, right? This will be nothing else. Usually it's defined by the max for all k between 0 and n between xk minus 1. And this is, in our case, it's the max, it's 1 over n, right? Because k minus n minus k minus 1 over k over n minus k minus 1 over n will be 1 over n. And this guy will converge to 0 as n approaches infinity, which is exactly what we want. So it's a nice division. And now we can consider the intermediary points, the intermediate points, let's say. These ck, which we can take them as k over n because these belong to this interval x sub k, x sub k minus 1, x sub k. And do not forget the fact that this is k minus 1 over n, and this guy is k over n. All right, that's beautiful. Now the Riemann sum, now we can form the Riemann sum as, let's call this Rn of fx associated to ck. So this will be the Riemann sum as 1 over n times the sum from k equals 1 to n of f of k over n. Well, which is in our case, like I said, we can write this as the sum for our function will be nothing else than just the sum from k equals 1 to n of 1 over 1 plus k over n. And this guy, as n approaches infinity, will converge to the integral from 0 to 1 of 1 over 1 plus x dx. And this guy, this integral here, but the integral from 0 to 1 of 1 over 1 plus x dx is nothing else than just ln of 1 plus x from 0 to 1, which gives us ln of 2 or log 2, whatever. So the final, so the result is nothing else than just log 2, ln of 2. So that's the final result of this limit, right? So that's a way to compute limits using Riemann sums. And pay attention, you need to make them look something like this. As you can see here, k over n, and you need to come up with 1 over n in front of it, or maybe 2 over n, some constant, because usually in the Riemann sums, as you can see here, we have b minus a over n, where b minus a is actually the length of the interval. All right. Now let me do more examples. Of course, I'm not gonna go into detail as in this problem. Although I would suggest when you have a problem in the Putnam and you want to write the solutions, the solution, I would suggest that you go into details just like I did here. Now, so that was problem number, well, an example. Now let's see another problem. So problem 2. And this problem was a Putnam problem. It's an old Putnam problem, but still. Putnam, I don't recall exactly what problem. I think it's classical example at this point, but in 1941. All right, so the question was, evaluate the following limit. And the limit was this limit as n approaches infinity of the sum from k equals 1 to n of 1 over the square root of n squared plus k squared. All right, so that's the problem. Well, indeed, maybe we can make this look like a Riemann sum again. So we will write this as this sum here. Right? We will write this as, again, we will do this trick always. We're going to take out 1 over n in front of the sum. And now let's see what do we get. So we have 1 over n, and this will be written as, is the same thing as in the previous example. The only difference is that we have a square root, so it's k over n, everything squared, and everything under the square root. And again, by the Riemann sums, right, by doing all this, you consider the function f of x to be 1 over the square root of 1 plus x squared and so on, but I'm just going to skip the details. And this will converge as n approaches infinity to the integral from 0 to 1 of 1 over the square root of 1 plus x squared dx, right? And this can be computed, but the integral from 0 to 1 of 1 over the square root of 1 plus x squared dx, this would be nothing else than just log is the antiderivative of 1 plus log of 1 plus x squared, right? The square root of 1 plus x squared from 0 to 1, and this would give us log of 1 plus square root of 2, right? All right. Wait, 1 plus square root of 2 minus, wait. When it's 0, log of 2, right? Log of 2. Or if you want, this would be log of, if we do the 1 plus square root of 2 over 2. All right, so that's the this limit. Now let's see another problem, which is of similar flavor. Problem 3, which says that this is a Putnam, more recent one, but still very old, Putnam B1 in 1970. Again, evaluate the limit as n approaches infinity of 1 over n to the 4th times the product from I equals 1 to 2n of n squared plus I squared, everything to the power 1 over n. So this is the problem. Again, you see now we have a product. So maybe we can consider, well, maybe there is a way to transform this product into a sum. And the only thing to do that is by just taking the natural log. So let's do that. So let's consider, so let an be this sum, this product, 1 over n to the 4th times the product. All right, and now then let us consider the following sequence, bn to be log of an. So we're going to take the log of this guy, right, which is 1 over n times, and now we're going to have the sum from I equals 1 to 2n, and now we're going to take the log. This would be log of 1 plus I squared over n squared. Well, at this point, if you look at this guy, clearly this represents the Riemann sum. So clearly this represents the Riemann sum. Right? For the function, and pay attention now because I'm going all the way from 1 to 2n. So for the function f defined on the interval 0, 2, and this will be real value, and the function is given by log of 1 plus x squared, sorry. So this is the function. Clearly this is a continuous function, is integrable, so I have no problems. So the limit as n approaches infinity of bn is nothing else than just the integral, right, by the Riemann sum from 0 to 2 of log of 1 plus x squared dx. And now this guy, well, you can do integration by parts if you want, but this is, okay, let's do it. The integral from 0 to 2, this is x prime log of 1 plus x squared dx, which would give us, integrating by parts, this would give us x log of 1 plus x squared from 0 to 2 minus the integral from 0 to 2 of x times log of 1 plus x squared prime dx. And this guy is nothing else than just, so this is 2 log of 5 minus the integral from 0 to 2 of x times, this guy is 1 over x, 1 plus x squared times 2x dx. And this is nothing else, 2 log 5 minus the integral from 0 to 2 of, okay, let me take the 2 out. So 2, and this guy will be x squared over 1 plus x squared dx. And now this would be, if you want to compute it, so this would be 2 log 5 minus 2. And now what I'm going to add and subtract 1. So this would be the integral from 0 to 2 of 1 plus x squared over 1 plus x squared dx. And I subtract 1, so this would be minus the integral from 0 to 2 of 1 over 1 plus x squared dx. Okay. And now I'll have here the arctangent, so this would be nothing else. Okay, I'm just gonna, let's see, so this is 2 log 5 minus 2 times, this guy is 1, so 1 is 2, minus arctangent of, right, arctan of x from 0 to 2. So this would give us finally 2 log 5 minus 4 plus 2 arctangent of 2. Okay, so that's the answer. I hope I didn't do any mistakes, but I don't think so. So this is the limit of Bn. Pay attention. So it's the log of this, right? So finally, the limit of An. So the limit as n approaches infinity of An is e to this, right? It's e to 2 log 5 minus 4 plus 2 arctangent of 2. Anyway, and you can do the computations by yourself. We're just gonna leave it the way it is. So that was a Putnam, well, it was considered to be the easiest problem in the Putnam back in the 70s, but still. All right, I think we had enough examples of how to deal with limits of functions involving Riemann sums. And I think throughout these 3 examples, I think you get the idea. Now I want to veer towards something else. So the second part of this lecture, I want to talk about the continuity of, so this first part was about the Riemann sums. Let's put it like this. And now for the second part, let's talk about the continuity of integrals. And you will see a bunch of techniques here. We'll see how to compute certain type of integrals, how to deal with functional equations involving integrals and so on. But before I go and do problems, I'd like to remind you a couple of things. So the first thing was this theorem, let's say theorem 1, which says that if, so let f be, in fact, let me write it here. Let f define in this way from a to b in real value, right? This be an integrable function. And f defined from a to b to r is given by f of x is this guy is the integral from a to x of f of t dt, right? For all x in a, right? Then this guy is continuous. Then f, capital F is continuous. So that's what you have to know. So once I have this integral from a to x, basically the antiderivative is continuous provided that f is integrable. Now the second theorem will tell you exactly what happens, how this will be related to the initial function. And let f, so we'll consider the function f defined on AB, or real value. This is an integrable function. Integrable, and I would say even more, maybe and continuous. At one point, let's say at the point x naught, I'll pick just an arbitrary point. The function f of x equals, again, we'll take the integral from a to x of f of t dt, right? And this is will be defined for all x in AB. This function is differentiable, right, at the point x naught, and moreover, f prime of x will be nothing else than just f of x. In other words, if I have a continuous function f, then the antiderivative, which is given by that f, the f of x, capital F of x, which is the integral from a to x of f of t dt, the derivative of this will give you the function f. And now as a consequence, let's consider f, let f be a continuous function. On the interval AB. The function f defined from a to b, AB to real value. F of x is the integral from a to x of f of t dt is differentiable for all x in AB, and moreover, f prime is f, right? So it's even more, it's differentiable. All right, so basically it tells you how to differentiate the integral. And I would like to show you some examples of this kind, because here one of the most important things is to, well, in these theorems, what is in disguise is the fundamental theorem of calculus, but I'm sure you guys already know that. And now I would like to do another problem 4, let's say. Which says, since we evaluated the limits of some functions, limits of sequences involving Riemann sums, now let's evaluate some integrals. So now we would like to evaluate this integral, the integral from 0 to pi over 4, pi over 2, I think. I don't recall exactly, but anyway, is of dx over 1. Let me look it up. Okay, so it's 1 plus tangent of x, everything to the power square root of 2. Anyway, so this was a Putnam A3 in 1980. Wow, A3. All right. As you can see that the number, the square root, put the exponent is might scare you, but you can just ignore it. Just you consider any. So what I'm going to do is the following. So let r be square root of 2. So and let's denote this integral and let I be the integral from 0 to pi over 2 of dx over 1 plus tangent of x, everything to the power r. All right. And now we would like to do some trick here and pay attention. Usually when you have integrals of trigonometric functions, right, try to do this trick. Try to change the variable from x to pi over 2 minus x. You see you have the upper bound of the integral to be pi over 2. So using the substitution, let's say x to be pi over 2 minus u, right, with the new variable. We have, let's see, what do we have? So dx will be negative du. When x is 0, u is pi over 2. When x is pi over 2, u is 0. So we have I, right, is the integral from pi over 2 to 0 of, so dx will be negative du over 1 plus cotangent. So, right, you see the tangent of pi over 2 minus u will be the cotangent of u, and everything to the power r. All right, so that's the integral with the new variable. which gives us, if you, well, with this negative here, this will be nothing else than just the integral from 0 to pi over 2 of du over 1 plus cotangent of u to the power r, which is nothing else than just the integral from 0 to pi over 2. And if we write this cotangent as 1 over tangent, so this would be tangent of power r of u over 1 plus tan of u du. All right, so we got all the way up to this point. So this is u. But now pay attention. Well, it doesn't matter. You can change the variables again. You can go back to x if you want. But you see, you have I to be this. But if you add them, let's see, what do we get? If you add them, if you add the initial integral with this integral, so adding up the two expressions, the two integrals for I, let's say, for I, we get, and let's see, what do we get? So we get 2I will be, if you add the first one, right, see up, and the last one, you will get that this is nothing else than the integral from 0 to pi over 2 of 1 plus tangent, and let's go back to the initial variable, tangent of x to the power, tangent to the power r of x plus over the same thing, dx, which is nothing else than the integral from 0 to pi over 2 of dx, right? It's 1 here. And this is nothing other than just pi over 2. So from here, the integral 2I is pi over 2, I will be pi over 4. And that's it, the end. So that was a trick. You see, you have this trick here. So keep this in mind. When you have to compute integrals with involving trigonometric functions, try to look for this. Well, of course, if you had the bound, let's say, if you had something different than pi over 2, let's say pi over 4, well, you can adapt. You can just take the substitute, you can use the substitution pi over 4 minus u, whatever. All right, now let's see another problem, and which is of similar flavor, the problem 5. And here I'll give you more solutions, problem 5. And this is find this integral, the integral from 0 to 1 of log of 1 plus x, everything over 1 plus x squared, dx. Right? So this was a Putnam A5 in 2005. So that was a... Now let me show you the official solution, and then maybe I'll show you 3 solutions. So solution 1, the official one. And it's a bit tricky, I would say, but once you see the other solution that I have in mind, you'll see that this would make sense. But anyway, let's go with the official solution. And here comes the trick. So let's make the substitution. So with the substitution, arctan of x equals t. So that's the substitution I'm going to make. The integral, let's call this integral I. The integral takes the form and let's see. So this will be the integral from, so I will be 1 plus x squared. So this would be nothing else than just the integral from 0 to pi over 4. Anyway, I'm going to, of log of 1 plus tangent of x. tangent of t, sorry, dt. Okay, so that's the, and now, since, as you have seen in the previous example, I'm going to do, since I transformed this into an integral involving trigonometric functions, well, why not play around with the same substitution? So now, with the substitution, and the substitution is t, let's say, is, maybe I should use some other, but anyway, u, let's say. No, actually, all right, it doesn't matter. T equals pi over 4 minus x, right? Our integral becomes the following. So this will be I is the integral from the pi over 4 to 0, right, of log of, and now let's be 1 plus tangent of pi over 4 minus t, and here I have a negative 1 here, let's not forget about that, times negative 1 dt. And this would be, if we put everything together, go back, this would be the integral from 0 to pi over 4 of log of, and now let's be careful here, so that would be 1 plus 1 minus tangent of t over 1 plus tangent of t dt, which is the integral from 0 to pi over 4 of log of 2 over 1 plus tangent of t dt. But this guy here is nothing else than just pi over 4 log 2 minus I. So clearly solving this for I, so I will give us nothing else than just pi over 8 times log 2. So this was more or less the official solution. I think you can find this also in the Putnam and Beyond book. But now let me give you another solution, solution 2, which is of similar flavor. And this solution, so it's an alternative way to the first solution. So I find it, well, to be honest with you, when I look at the first solution to do this substitution, the change of variables, arctan of x equals t, is not quite handy. So what I would do is to see it in a clearer manner, I would just integrate by parts. So integrating by parts, we get, so we would have that the integral, let's look, and let's call this I, of log of 1 plus x over 1 plus x squared dx. This would be, and let's write it in, log of 1 plus x squared, and now you can see that 1 over 1 plus x squared is nothing other than just the arctangent, the derivative of arctan of x, and this would be equal to, let's write it here, so this would be log of 1 plus x squared times arctan of x from 0 to 1, right, minus the integral from 0 to 1 of arctan of x over x plus 1 dx, right. So, oh, sorry, here it's 1 plus x here. All right, which will give us, this is, if we plug it in, so this is pi over 4 log 2 minus this integral, right? Minus the integral from 0 to 1 of arctan of x over x plus 1 dx. So now let's denote by j this integral. And now let's play around with it. So now it looks a little bit more human. And I'm going to do the same trick using the substitution. And now arctan of x equals, you see now it's equals u. We obtain that this our integral j, that j is the integral from 0 to pi over 4 of u times 1 plus tangent squared of u, and everything over 1 plus tangent of u du. And now again with the substitution, pi over 4 minus u equals y. We get, let's see, what do we get? So we get that j, this integral. So let's keep this in mind. You see, it's kind of similar to the official solution. The only difference is that I don't come up with that surprise substitution arctan of x equals u right from the beginning. So that's why I integrate by parts. I would say this is more human. So now we will have that j will be the integral from 0 to pi over 4 of, and now let's see, u will be pi over 4 minus y, right? And this would be 1 plus tangent squared of y, everything over 1 plus tangent of y dy. And this guy would be, so let's do some algebra here. So this is the integral of pi over 4 times the integral from 0 to pi over 4 of 1 plus tangent squared of y over 1 plus tangent of y, right? Minus j. Okay. But now the only thing we're left to deal with is this integral here, right? So finally, this implies that let's see, that 2j will be equal to pi over 4 times the integral from 0 to pi over 4 of 1 plus tangent squared of y, everything over 1 plus tangent of y dy. But this guy here is nothing else than just, let's see, so this is pi over 4 times, this is nothing else than just the log, the natural log of 1 plus the tangent of y from 0 to pi over 4. And this would give us nothing else than just pi over 4 log 2. So from here, j will be nothing else than just pi over 8 log 2. And that's the final answer. You see, it's similar to the official solution, but it's more human, I would say. See, we got the same result here as well. And now I'm going to show another solution, the third one. So solution number 3. So I'm going to show you something which is called Feynman trick. So this is one of the Feynman tricks to compute integrals. And what we're going to do is we're going to introduce a parameter inside the integral. So we will define the function, and we're going to define it the following way: f of t to be the integral from 0 to 1 of log of 1 plus x times t, everything over x squared plus 1 dx. You see, that's, I'm going to introduce the parameter t inside there. So such that, so that f of 0 is 0, right? That's clear. And the desired integral is nothing else than just f of 1. Is f of 1. So we need to compute f of 1. That's what we're interested in computing f of 1. All right, so now let's differentiate. So differentiating under the integral, we get so we have, let's see, f prime of t will be, so it will be the integral from 0 to 1 of, so that will be x over x squared plus 1 times 1 plus xt dx. All right, so that's the derivative, right? Okay, now by partial fractions, because we can write this inside the integrals of as a partial fraction, by partial fractions, and I'm going to skip the details, we have, let's see, so we have that f prime of t. Let me see, what did I do? I did some computation somewhere here. Okay. So by partial fractions, this would give us 2t arctangent of x. I'll leave this to you as an exercise here, since I don't want to do computations like crazy. Minus 2 log of 1 plus xt plus log of x squared plus 1, right? Everything over 2 times t squared plus 1. And this is taken from x equals 0 to x equals 1. From 0 to 1. So let's not forget about that, right? I hope these computations are correct. So this would give us nothing else than, okay, let me copy it all the way, plus 2 log 2 minus 4 log of t plus 1. And everything over 4 times t plus 1, t squared plus 1. All right, so that's f prime of t. And now the only thing we need to do is to integrate. So we're going to integrate with respect to t now. So integrating with respect to t, we have f of t is log 2 arctangent of t over 2 plus pi log of 1 plus t squared over 8, and minus, and here we'll see, okay, so I have this integral. Wow, that's nice. The integral from 0 to t of, let's just say, log of 1 plus s over 1 plus s squared ds. Well, as you can see now, this is nothing else than just our integral, which is absolutely great, right? And now let's evaluate at t equals 1, because that's what we're interested in. We have that f of 1 is nothing else than just pi log 2 over 4 minus the integral from 0 to 1 of log of 1 plus s, everything over 1 plus s squared ds. Again, So this is again f of 1. So this will be equivalent with 2f of 1 is pi log 2 over 4. So f of 1 is nothing else than just pi log 2 over 8. And that's the final answer. Wow, this is a very nice trick. So you see, you have seen 3 ways. I think there are plenty of other solutions. At some point, when we will talk about multivariable calculus, I'll go back to this problem because I want to show you another solution using Fubini's theorem. So I'm going to integrate with respect to 2 variables. But anyway, we'll get there. So I'll go back to this example. And I'm sure there are plenty of other solutions using series expansions and so on. So you have seen 3 solutions for this one. So now let me veer towards another problem. Sorry about that. Now let's see, what was this problem number 6? Again, this was an old Putnam problem in 1947, so right after the war, which says the following. So let me consider f real valued and define on R such that, well, is differentiable, right? Such that f of 1 equals 1, and for x greater or equal than 1, we have that f prime of x is more like a differential equation. Looks like x squared, 1 over x squared plus f squared of x. Show that the limit as x approaches infinity of f of x exists, and it is less than one plus pi over 4. So that's the statement of the problem. Again, this is just an application of the fundamental theorem of calculus if you want. But now let's look at this, right? So you see we have this here, right? We have this guy here. So let's analyze this a bit. Well, the quantity on the right-hand side is clearly negative, positive, I would even say, right? And well, clearly, oops. So clearly, f prime of x is positive for all x greater or equal than 1. So f is increasing. Right? Okay, that's great. So its f is increasing on the interval 1 positive infinity. Okay, that's great. So f of x is less or equal than f of 1 whenever x is greater or equal than 1. Anyway, less strictly. Then we have, so now let me change a bit the variable. Then we have that f prime of t, which is given by 1 over t squared plus f squared of t. This guy will be less than, so I know that 1 over t squared plus 1. Right? That's obvious. Because f of 1 is 1. Let's not forget that. So this guy is 1 here. All right, for all t greater than 1. And now, now we have that f of x, which is 1 plus the integral from 1 to x of f prime of t dt. So this guy will be less than 1 plus the integral from 1 to x of, and now I know that f prime is less than this, so I'm going to use this inequality. So this will be 1 over t squared plus 1 dt. And now let's be careful here. This will be, and I'm going to avoid an improper integral, so I'm to say exactly what it is, but I'm going to write it in this way. So it's less than 1 plus this guy, the limit as n approaches infinity of the integral from 1 to n of 1 over 1 plus t squared dt. Because, right? Well, in this guy, it will, if you compute it, so this will be the arctangent, so this will be 1 plus pi over 4. Well, since f is increasing and bounded, right, it follows that the limit, so the limit as x approaches infinity of f of x exists. And therefore, the limit as x approaches infinity of f of x is 1 plus the lim as n approaches infinity of the integral from 1 to n of f prime of t dt, right, which is less than 1 plus the lim as n approaches infinity of the integral from 1 to n of 1 over 1 plus t squared dt. And this guy is nothing else than just 1 plus pi over 4. And that's the end of the problem. Anyway, it's a very nice problem, very easy, I would say. But I think I remember when I was preparing for, when I was in my graduate studies some time ago, and I was preparing for the preliminary exam problem. I think this popped up in the quite often. So also it was given at Berkeley preliminary exam, so I think you can find it in the Berkeley book. So just like I said, there are some problems taken from old Putnam exams and put them, and they're put into preliminary exams at different universities, or qualifying exams, whatever you want to call them. All right, so that was a problem, very nice problem. And now let me draw your attention with the very, very last problem. And after this, I think I will stop. Problem 7. Very beautiful problem, I remember it. I think it was some kind of Romanian National Mathematical Olympiad, 2002, which says the following. So let me consider a function defined on R and real value. So be a continuous. This is a continuous function and bounded. All right. Show that if the following condition holds, if the x times the integral from x to x plus 1 of f of t dt is the integral from 0 to x of f of t dt for all x in R, then f is constant. So that's the problem. It's a very nice problem. Well, as you can see here, we have a functional equation involving integrals. In other words, antiderivatives. So we would like to write that. So let's now let's consider f defined on 0 infinity, real value, by f of x to be the integral from 0 to x of f of t dt for x non-negative. So our condition can be rewritten as x times f of x plus 1 minus f of x, right, by the fundamental theorem of calculus, and this guy will be f of x minus f of 0, again, by the fundamental theorem of calculus, but f of 0 clearly is 0, so it's just f of x. Or, equivalently, we can rewrite this as, okay, so equivalently, this is x times wait. So okay, I had to subtract 1, so x plus 1 minus all right, so this will be x times f of x plus 1 is x plus 1 times f of x, right? So I can write it in this way. Or even more, and this is where I wanted to get to, f of x over x is f of x plus 1 over x plus 1. All right, so this is the essential. So by just now, let me consider the function. So consider the function g, and I will define g in the following way. G of x to be f of x over x, right? For x positive. All right, clearly g is differentiable. And moreover, g prime of x, if we compute the derivative by using the quotient rule, so this would give us x f of x minus capital F of x, everything over x squared. Or if you want, this would be written as f of x over x minus capital F of x over x squared. Now, clearly, if you look, I'll leave this to you as an exercise. So next, we observe that both a g and g prime are periodic with period 1. Okay, so we can write this, so we can write, and let's see, so we can write that x times g prime of x is f of x minus f of capital F of x over x, and this is nothing other than just f of x minus g of x. So, which is equivalent with what? With the fact that f of x is nothing other than just g of x plus x times g prime of x. All right, so we have this. And this happens for all x positive. All right, great. This is another relation that we will want to take into account. Because from here, by an easy induction, so by an easy induction, we have that, so we obtain, let's say, that what? That f of x plus n is nothing else than just g of x plus x plus n times g prime of x. And this will happen for all x positive and for all n greater or equal than 0, right? Again, let's keep this in mind. Let me denote this by star, because and now what we're going to do is to prove that the derivative of g is 0. So we show that g prime of x is 0 for all x. All right. Assume that is not. So assume that there exists x naught positive such that g prime of x naught is not 0, right? And we'd like to obtain a contradiction. All right, but by looking at star, by star, if we take the limit as n approaches infinity, we have that the lim as n approaches infinity of f of x naught plus n is nothing else, if we plug it in here, right, by star is nothing else than just infinity. Well, plus minus infinity, depending on how it's positive, how g of x naught is, positive, negative, so on. G, the derivative, right? If it's positive, it will be positive infinity. If it's negative, it will be negative infinity. It doesn't really matter. It's plus minus infinity. But this is in contradiction. So in contradiction with the fact that f is bounded. Right? So therefore, the derivative for all x, for all positive x, is 0. So this implies that, so therefore, g prime of x is 0 for all x positive. And from here, clearly it will, so since g prime of x is 0, then we'll have that f will be g, right? So this is nothing else than just f constant. So f on the interval 0 infinity restricted to this will be constant. Well, because we talked only about when x is positive. So similarly, f on the interval negative infinity 0 will be constant. So the conclusion follows. Right? All right. Okay, I think this sums up what we what I wanted to cover for this lecture. Next time I will be talking about the mean value theorem for integrals. There are 2 of them. In fact, there are 3 of them, but I will talk only about 2 of them. And you'll see a bunch of applications as well. But also, I'd like to talk about integral inequalities. And then a third lecture will be devoted to a series of functions, sequences of functions where I will involve integrals. So in other words, we will see how to pass the limit inside an integral. All right, I'll stop here. Thank you very much.